National Electrical Code, specifically Section B310.60.C.2.b, addresses ampacity derating factors for cables installed at deeper depths. This section allows a 6% derating factor per foot for depths below 2 feet. This means that for every foot of depth beyond the initial 2 feet, the cable's ampacity is reduced by 6%. However, applying this linear derating factor can lead to impractical results, especially for very deep installations. For instance, as mentioned, if a cable is installed at a depth of 16.6 feet, the calculation would suggest a zero ampacity, which is unrealistic. To address this, the National Electrical Code provides an alternative approach through engineering supervision, as outlined in Section B310.60.C.2.b. This allows for a more realistic ampacity determination that considers the specific conditions of the installation. Engineering supervision involves a detailed analysis of the installation environment and cable characteristics to determine a suitable derating factor. One common method used under engineering supervision is the formula ampacity equals base ampacity times derating factor to the power of depth. Here, the base ampacity represents the cable's ampacity at the 2-foot depth mark. The derating factor is a value, typically less than 1, that accounts for the reduction in ampacity due to depth. Depth is the depth of the cable installation measured in feet. The derating factor is generally determined through empirical data or engineering analysis, and it often increases with depth up to a certain point, after which it stabilizes. Now let's consider the meaning of the phrase "shall be permitted" in the National Electrical Code. This phrase indicates that the provision is optional, not mandatory. In the context of ampacity derating, it means that the engineer has the option to use the 6% per foot derating factor or to conduct a more in-depth engineering analysis to determine the cable's ampacity. It's not a requirement to use the 6% rule, especially when it leads to unreasonable results. When presenting ampacity calculations to an electrical inspector, clarity and thoroughness are essential. It's important to provide a clear and concise explanation of the methodology employed, including all assumptions made. If engineering supervision was used, ensure that you have sufficient documentation to support your calculations. This documentation might include empirical data, engineering analyses, or manufacturer specifications. The inspector needs to be able to understand the rationale behind the calculation and be convinced that the calculated ampacity is reasonable and safe for the specific installation. If there are any disagreements or concerns, a technical discussion should be held to reach a consensus and address any potential issues. Here's a deeper dive into ampacity and how it relates to cable installations. Ampacity, short for ampere capacity, refers to the maximum amount of electrical current, measured in amperes, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. This rating is crucial for ensuring the safe and reliable operation of electrical systems. Exceeding a conductor's ampacity can lead to overheating, insulation degradation, and potentially fires. The National Electrical Code provides tables and guidelines for determining the ampacity of various types of conductors based on factors such as conductor material, size, insulation type, and installation conditions. These tables are a starting point for determining the appropriate conductor size for a given application. However, various factors can affect a conductor's ampacity, requiring adjustments or derating. These factors include ambient temperature, the number of conductors in a raceway or cable, and the presence of thermal insulation. Ambient temperature refers to the temperature of the environment surrounding the conductor. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thus lowering its ampacity. The National Electrical Code provides correction factors to adjust ampacity based on ambient temperature. When multiple current-carrying conductors are installed in close proximity, such as in a raceway or cable, the heat generated by each conductor can raise the temperature of the surrounding conductors, reducing their ampacity. The National Electrical Code provides adjustment factors to account for the number of conductors in a raceway or cable. Thermal insulation, such as that used in walls or ceilings, can impede the dissipation of heat from conductors, reducing their ampacity. Conductors installed in thermally insulated environments may require additional derating. The depth of underground cable installations can also affect ampacity, as discussed earlier. The National Electrical Code provides guidelines for derating conductors installed at depths greater than 2 feet. In some cases, conductors may be installed in environments with corrosive substances or other factors that can degrade the conductor or its insulation. These conditions may require the use of specialized conductors or installation methods. Proper ampacity calculations are essential for ensuring the safe and reliable operation of electrical systems. Failure to properly account for all relevant factors can lead to overheating, insulation degradation, and potentially fires. Engineers and electricians should carefully review the National Electrical Code and other relevant standards to ensure that ampacity calculations are accurate and appropriate for the specific application. Let's consider a practical example of ampacity derating. Suppose you have a 12 American wire gauge copper conductor with THHN insulation installed in a raceway with an ambient temperature of 40 degrees Celsius. The conductor is part of a circuit with 6 current-carrying conductors in the same raceway, and the installation depth is 5 feet underground. Firstly, determine the base ampacity of the 12 American wire gauge THHN conductor from the National Electrical Code Table 310.60.C.2.b. Assuming the conductor is rated for 90 degrees Celsius, the base ampacity is 30 amps. Secondly, adjust for ambient temperature. The National Electrical Code Table 310.15.B.2 provides correction factors for ambient temperatures other than 30 degrees Celsius. For an ambient temperature of 40 degrees Celsius, the correction factor is 0.87. Multiply the base ampacity by the correction factor to get the adjusted ampacity. 30 amps times 0.87 equals 26.1 amps. Thirdly, adjust for the number of conductors. The National Electrical Code Table 310.15.B.3 provides adjustment factors for the number of current-carrying conductors in a raceway. For 6 conductors, the adjustment factor is 0.80. Multiply the adjusted ampacity by the adjustment factor to get the further adjusted ampacity. 26.1 amps times 0.80 equals 20.88 amps. Fourthly, adjust for depth. According to the National Electrical Code section B310.60.C.2.b, a 6% per foot derating factor applies for depths below 2 feet. The cable is installed at 5 feet, so the depth below 2 feet is 3 feet. The derating factor is 1 minus 0.6 times 3, which equals 0.82. Multiply the adjusted ampacity by the derating factor to get the final ampacity. 20.88 amps times 0.82 equals 17.12 amps. Therefore, the final ampacity of the 12 American wire gauge THHN conductor under these conditions is 17.12 amps. It is important to note that this is just an example, and the specific conditions and National Electrical Code requirements may vary depending on the application. Always consult the latest edition of the National Electrical Code and other relevant standards for accurate ampacity calculations. Now let's explore some additional considerations for ampacity derating. Firstly, harmonic currents. In electrical systems with nonlinear loads, such as electronic devices and fluorescent lighting, harmonic currents can be present. Harmonic currents can increase the temperature of conductors, requiring additional derating. The National Electrical Code provides guidelines for derating conductors carrying harmonic currents. Secondly, voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction and can also increase the current drawn by the load, potentially exceeding the conductor's ampacity. The National Electrical Code provides guidelines for limiting voltage drop in branch circuits and feeders. Thirdly, continuous loads. A continuous load is a load that is expected to operate for 3 hours or more at a time. The National Electrical Code requires that branch circuits supplying continuous loads be derated to 80% of their rated ampacity. This is to prevent overheating of the conductors. Fourthly, equipment terminals. The ampacity of conductors is also limited by the temperature rating of the equipment terminals to which they are connected. The National Electrical Code requires that conductors be sized so that their ampacity does not exceed the temperature rating of the terminals. Fifthly, conductor insulation. The type of insulation used on a conductor affects its ampacity. Conductors with higher temperature rated insulation can carry more current than conductors with lower temperature rated insulation. The National Electrical Code provides tables of ampacity for various types of conductor insulation. Sixthly, conductor material. The material of which a conductor is made also affects its ampacity. Copper conductors have a higher ampacity than aluminum conductors of the same size. The National Electrical Code provides tables of ampacity for both copper and aluminum conductors. Seventhly, grounding conductors. Grounding conductors are used to provide a path for fault current to return to the source. Grounding conductors must be sized according to the National Electrical Code to ensure that they can safely carry the maximum fault current. Eighthly, surge protection devices. Surge protection devices are used to protect electrical equipment from voltage surges. Surge protection devices can generate heat when they are operating, so it is important to ensure that they are properly sized and installed. Ninthly, renewable energy systems. Renewable energy systems, such as solar and wind power systems, can have unique ampacity considerations. The National Electrical Code provides specific requirements for the ampacity of conductors in renewable energy systems. Tenthly, energy storage systems. Energy storage systems, such as batteries, can also have unique ampacity considerations. The National Electrical Code provides specific requirements for the ampacity of conductors in energy storage systems. Ampacity calculations are an integral part of electrical design and installation. Accurate ampacity calculations help to ensure the safe and reliable operation of electrical systems. Engineers and electricians should carefully review the National Electrical Code and other relevant standards to ensure that ampacity calculations are accurate and appropriate for the specific application. In summary, ampacity derating is a critical aspect of electrical safety. It involves reducing the allowable current carrying capacity of a conductor due to various factors such as ambient temperature, the number of conductors in a raceway, and installation depth. The National Electrical Code provides guidelines and tables for determining ampacity and derating factors. When presenting ampacity calculations to an electrical inspector, it is important to provide a clear and concise explanation of the method used and the assumptions made. If engineering supervision was used, be prepared to provide documentation to support your calculations. The inspector should be able to understand the rationale behind the calculation and agree that the ampacity is reasonable and safe for the specific installation.